Hello again, thank you for joining part 2 of my talk. Now I want to talk about maximal surfaces in the Heisenberg group using loop group methods. So first I want to introduce the loop group methods for harmonic maps, especially harmonic maps in the sphere, which will be relevant, and I'm going to use the example of constant positive Gauss curvature surfaces, also known as spherical surfaces. So a spherical surface, by a spherical surface I mean specifically constant positive curvature K equals 1 here. For example, the sphere itself. And here are some other examples which you might have seen before. These are spherical surfaces of revolution, which you can easily obtain by figuring out what the profile curve should look like for such a surface if the curvature is constant. Here are some more difficult to obtain examples which have been found using loop group methods. In some recent work that I've been doing with Pedit, we have been looking at the singularities of these surfaces. The issue here is spherical surfaces are what's called fronts, and the wavefronts, and the singularities and bifurcations of wavefronts are known to be respectively. Generic singularities are cuspal edges and swallowtails, and the generic bifurcations or codimension 1 singularities are these 5 singularities here. So even though spherical surfaces are wavefronts, we can show that not all of these singularities even occur at all for spherical surfaces. So that's why there's an issue about classifying these singularities. So the method I want to introduce is connected with harmonic maps. So and the type of methods which I'm going to talk about apply to most of these surfaces. So I just want to give you an introduction to the general setup. So the starting point is that many important classical surfaces correspond to harmonic maps into symmetric space. These can also be Lorentzian harmonic, but I'm just talking about Riemannian harmonic maps today. So for example, constant mean curvature surfaces, constant Gauss curvature surfaces, and Willmore surfaces. These are the most well-known examples. Let's just look at the specific case of spherical surfaces. A map from C into S2 is harmonic if and only if it satisfies this equation, that this kind of Laplacian of n is parallel to n, so that the tangential part is 0. And you can easily check that this is equivalent to the integrability condition for this differential equation for f. So if you have a solution for the harmonic map equation, then you can solve this equation for f. Then you can check that this map f at any point where it's regular is a constant curvature k equals 1 surface in R3. And conversely, every constant positive curvature surface can be represented this way. So spherical surfaces, or in fact generalized spherical surfaces which may have singularities, are in one-to-one correspondence with these harmonic maps. And so you can see on these images here that the types of singularities that you get, since we talk about singularities, are not the same. So for this type of surface, you can see that the spherical surface has a singularity if and only if the harmonic map does. But this is not always the case for these kind of integral geometries. But nevertheless, even though that's true, the types of singularities you get are different for the spherical surface f and the harmonic map n. So the loop group methods for constructing solutions goes like this. So first of all, you have a symmetric space represented by a Lie group G and K, a fixed point subgroup with respect to some involution sigma. So G would be a semi-simple Lie group. Just think of the example for this talk, just think of the example that G is SU2 and the complexification GC is SL2C. So from this information we construct a loop group or a subgroup of the general loop group. So the group of loops which are maps from S1 into the complex Lie group with some condition which for the purposes of this talk you can just think of these as being maps which extend analytically to an annulus around S1. Then the symmetric space information is encoded in a subgroup by extending this involution sigma by a formula that looks like this. And the real form information is encoded by saying that we look at the subgroup which take values in the real form G. So that's finally this group here. Here's an example. So G is SU2 and GC is SL2C, and this is an element of the exactly this twisted subgroup, because this matrix here, when lambda is in S1, lambda inverse is the same as lambda bar. So this is B minus B bar. This object has determinant 1. So it takes values in SU2, and the twisting condition, if you work out what this actually means for the relevant involution, which we're talking about today, it means that off-diagonal elements of this matrix should be odd powers of lambda, and diagonal elements should be even powers. So this is just one example. Now, how to construct harmonic maps or represent harmonic maps with this loop group? So suppose you have harmonic maps. Suppose you have a harmonic map from a subset U of C into G over K. That's what we want to represent. So I claim that these are characterized by maps from U into this loop group, this twisted subgroup of the loop group, which have this special property. So the Mercatin form, this F inverse is the matrix inverse of F. So this is the pullback to the Lie algebra of the Mercatin form. This is the pullback via F of the Mercatin form of the Lie group. So this object here would in general be an infinite Laurent expansion in lambda. And here you would have, generally you would have dz and dz bar if you expand it out in complex coordinates. So what you're looking at here is a very special map, because it only has these 3 terms here, and it only has dz here and dz bar here. So what you can show is that if you take such a map into the loop group, you evaluate it at some S1 value of lambda. So that gives you a map into G, and then you project to the symmetric space G over K that map, little f, will be a harmonic map, and conversely every harmonic map can be represented this way. So I'm not going into the explanation for this, but this is well known, which goes back to the 1980s. So we'll call such a map into the loop group an admissible frame, and the problem of constructing harmonic maps is exactly the problem of constructing admissible frames. So in the theory of loop groups there are a few different ways to construct these admissible frames, and I'm going to just describe one of them, which will be the DBW method. So to describe that, what we need is 2 decompositions of the loop group. First one is the Birkhoff decomposition. So we look at 2 subgroups of the loop group, lambda plus and lambda minus. So these correspond to elements of the complex loop group which extend holomorphically respectively to the unit disk and the complement of the unit disk in lambda. So the Birkhoff decomposition says that the product of these 2 subgroups is open and dense in lambda GC. Well, at least this is the case for SL2C. In other words, almost every element in the loop group can be factorized. X equals x minus times x plus, where x minus extends holomorphically to the exterior disk and x plus extends holomorphically to the interior disk. Here's an example just to illustrate what I mean. So this is some element of lambda SL2C. It's actually in the twisted group. And I've written it as a product of something which this one extends holomorphically in lambda inverse. This one extends holomorphically in lambda. An analog of this in finite dimensions is the LU decomposition of matrices into lower and upper triangular matrices. The other decomposition is the Iwasawa decomposition. This says that every element of the complex loop group can be decomposed into something which takes values in the real group times something which extends holomorphically to the unit disk. Here's an example. This is an element of the complex loop group, and I've written it as this one times this, and this one, if you check, well, this is the case SU2, this one takes values in SU2 when lambda is in S1, and this one extends holomorphically to the disk. And here's another example you can look at if you like. So this decomposition is an analog to the QR matrix factorization into Q is something in SUN or a UN, and R is a upper triangular matrix. So the DPW method uses these two decompositions to connect admissible frames, which is what we want to construct, to holomorphic maps, rather general holomorphic maps. Which is why this is sometimes called the generalized Weierstrass representation, because it's similar to the Weierstrass representation for minimal surfaces. So suppose you have I'll just explain what the statement is. Suppose you have an admissible frame as a map into the twisted subgroup of the loop group. It's characterized by this expression for the Marquardt form. So at each point Z in the domain U, perform a Birkhoff decomposition into F minus times F plus. That was the first decomposition I mentioned before. And then the claim is that F minus, the Marquardt form of F minus, is like this. It's extremely simple. It only has one term. The Laurent expansion in lambda only has one term. And it's holomorphic. So this B minus 1 is holomorphic in Z. You can check that by writing F minus in two ways. So first of all, the Birkhoff decomposition is done with a normalization that at lambda equals infinity, it should take value as the identity. This is actually what makes one way to make the Birkhoff decomposition unique. And also, if you take this this normalization, then the two factors, F minus and F plus, they will depend analytically on F, which means that if F is differentiable, so will each of these factors be. So we can compute the derivative of F minus here, like this. And if you look at the Laurent expansion, it's all negative powers of lambda here, plus a constant term. When you differentiate that, that becomes 0. So you end up with an expansion that looks like this for the Marquardt form. The highest power of lambda is -1. Now write F minus in a different way via the Birkhoff decomposition. F minus is equal to F times F plus inverse. Then compute the Marquardt form in terms of those two. So we know the Marquardt form of F. It's this expression up here, and we know that F plus it's holomorphic on the disk, so its expansion on S1 only has positive powers of lambda. So we end up with something that looks like this. The first term from F inverse dF was this one, and then everything else is higher order in lambda. So the conclusion is that if we compare this with this, that there is only one term there, and since we only have dz here, we don't have dz bar, that's the same as saying that d bar of f minus is 0. So f minus is holomorphic, which is the same as saying that this function b minus 1 is holomorphic. So every admissible frame gives you, by this decomposition, this so-called normalized potential. So this b minus 1 is just a 2 by 2 matrix because of the twisting condition, it just has the two off-diagonal terms, so two holomorphic functions essentially. Now the other direction, so did I say that? Yeah, so the other direction is given a one form, a holomorphic one form in the complex Lie algebra for the loop group, where the lowest order term is minus 1, and you can have as many other terms as you like here, and these are arbitrary holomorphic functions, these bn's. We solve this differential equation with some initial condition at some point, perform the Iwasawa decomposition, and this f, this factor, which takes values in the real subgroup of the group, you can check that this f will be an admissible frame. I won't go through the computation, but it's very similar to what I just did for the first direction. So finally, given an admissible frame, well, you know that you could project to S2 to get a harmonic map in S2, and then you could solve that differential equation by integrating it to get f. But you can also do another thing which is more convenient, and that's you can show that this formula here, directly from the loop group frame f, gives you a spherical surface which has the harmonic map n as its Gauss map. So this is the overall method which you can implement numerically. You take what's called a holomorphic potential, something that looks like this. These AIs are arbitrary 2 by 2 matrices, well, with the twisting condition here that the even powers of lambda are diagonal, the odd powers are off diagonal. Then you integrate this. This is automatically integrable. Then, so now you have a map into the complex loop group. Then you perform an Iwasawa decomposition, and then you perform that sim formula that was on the previous slide. And you can implement it by representing a loop in this way. So you take your loop, you cut your loop off the Laurent expansion to a polynomial, say from minus n to n. Then you write these are 2 by 2 matrices, you write these out in a long row here, a minus n up to an. Then you repeat this row shifted one space to the left above and one space to the right below. So you have this diagonal band matrix. Then you can check that if you multiply two of these together, that's exactly the same as multiplying two of these together, these Laurent polynomials. And you can check that the Birkhoff decomposition is exactly the same as the LU decomposition of such a matrix. So all of this can be coded on a computer, and you can compute the solutions. If you find my homepage on the internet, there's a link for math software, and you can find code for computing various integrable surfaces. For example, K1 surf here will allow you to compute spherical surfaces, and there's if you click on this link here, you get instructions about exactly how to do it. The problem is, how do you choose the potential, eta? This is in the first step here, eta. How do you choose that to get a particular geometry? Here are some examples where I took the simplest possible potential. Eta is just one term, and two holomorphic functions. And in these examples, these are some choices for these holomorphic functions. Here are some more examples here. You can show that if these polynomials have certain properties, then you can get symmetries of finite order symmetries of particular orders here. And that's what I've done here. So what I've done with these surfaces is you can see that wherever we get a singularity, I've colored the surfaces so that the surface changes color at a point where the corresponding CMC surface has zero curvature, and such a point corresponds to a singularity of the spherical surface. So this helps us to see more clearly where the singularities are for these surfaces. Okay, so here's a summary again of the DPW method for spherical surfaces. Start with the holomorphic potential, integrate it, Iwasawa decompose, sim formula, and we can construct all spherical surfaces this way. So the limitation is that geometric information is lost in the Iwasawa splitting, or in the Birkhoff splitting if you go the other direction. So it's not easy to read off the geometric information from the potential. But if we want to solve geometric problems, there is something we can exploit, and that is that a given surface, there are many possible potentials. So for example, the normalized potential, that's the one with one term, this is what you get by choosing a normalization of the frame, the admissible frame at a particular point, Z0, and then computing the Birkhoff decomposition, as I showed you before. That's unique if you choose once you choose the point Z0. Another potential which is useful, which I've been using to solve the Cauchy problem for these surfaces, is what I call a boundary potential. It has three terms and it has a reality condition along a particular curve, and this curve is the curve where you want to solve your Cauchy problem. So I'll explain briefly how you do that. So what's a geometric Cauchy problem? The idea of a geometric Cauchy problem is to prescribe sufficient information along a curve, geometric information along a curve, to produce a unique solution to some geometric problem. For example, Bjorling's problem, if you prescribe the normal, what you want to be the normal of the surface along some curve, some space curve, then you get a unique minimal surface. So this is the example you get from this normal vector field here. And what's more, there's a nice formula for it. So if the curve, the prescribed curve was alpha, and the prescribed normal was n, then if you extend those holomorphically away from the curve, so everything should be real analytic here. If you extend them holomorphically away from the curve and then compute this formula, take the real part, then you get a formula for the solution. And this is based on the Weierstrass representation for minimal surfaces. So we can solve this problem also for surfaces connected to harmonic maps in this way. First of all, using the DPW method. First of all, remember we have that our construction via the DPW method was the input was a holomorphic, what's called a holomorphic frame. So you take this potential, integrate it, and you get a holomorphic frame. Then you perform an Iwasawa decomposition, and that gives you an admissible frame F. And as I said, there are many choices of potential, hence of this complex frame phi. So the idea is to find a potential that makes this Iwasawa decomposition trivial along the curve. Trivial meaning that phi is already in the real form, so that phi will be equal to f along that curve. Because if you do that, if the geometric information determines f along that curve, then it also determines phi, because we've chosen it so that f equals phi along that curve. You can actually do that. So here's how you would do it for spherical surfaces. You want to solve the Cauchy problem with, say, a prescribed normal n. So first of all, you choose coordinates so that your curve is given by y equals 0. So this means, of course, you can do this if your curve is an open curve in C, not a closed curve. Then you prescribe sufficient information to construct the loop group frame, well, let's call it f0 of x, along y equals 0 from gamma and n. It's possible to do that. I'm not going to write it down here, but you can do that. So now you have the Morikatan form of this extended frame along the curve. It will look like this. This is similar to what we had for an admissible frame, but because it's just along a curve, you have dx instead of dz here and dz bar there. Now we extend all of this holomorphically, and if you just look at this, you will see that I have holomorphic function here, holomorphic function here, and dz here. This satisfies the condition of being a holomorphic potential for the DPW method. Let's call it eta. So we can take this as a potential in our DPW method, integrate it, perform the Birkhoff the Iwasawa decomposition, and we have an admissible frame f. Then, since this this one form eta was unitary, was was real along the real line, this decomposition will be trivial along the real line. H plus will be the identity when y equals 0. So phi will be equal to f along y equals 0. And that means that f, this is the solution that we've constructed, will be equal to f0 along the original curve. So we have solved our geometric problem. So here's just one example of the kind of things you can do with this. So I was talking about singularities earlier. We can construct a surface with a prescribed singular curve using this method. So suppose you have a space curve which is defined by a curvature function and a torsion function. This is equivalent to a space curve. And let's assume that the curvature is not equivalent to 0. Then we take these functions, kappa and tau, they should be analytic, extend them holomorphically. Then, okay, so these E1 and E3 here, these are some basis vectors, basis matrices for the Lie algebra SU2. Then we take this as a potential for a spherical surface, and this gives you the unique spherical surface that contains the corresponding space curve as a singular curve. So this is just an example of how you can use these boundary potentials to solve geometric problems. So let's talk a little bit about the generic singularities of spherical surfaces. Remember, I said that these are a case of wavefronts. So what's known, there are the conditions for the generic singularities and bifurcations that I showed you on the earlier slides. There are recognition criteria for those, and I just want to give you a couple of examples here. So suppose you have a wavefront f with normal n. Set eta to be the null direction, so it's essentially a vector field of df, so it's the kernel of df. Set mu to be the the inner product of the cross product, well, let's say the scalar triple, this is not really, the inner product of the what should be the normal of f with n. So this function mu will determine when f is not immersed. So singularities correspond to mu equals 0. And the order of vanishing of mu tells you something about how bad the singularity is. So then you have criteria for two of the bifurcations, cuspidal butterfly and cuspidal beaks, given in terms of eta and mu. So we use such criteria to characterize the singularities for spherical surfaces, and I won't give the details, but I just want to mention that this is the type of criteria that we're using here. So using that, we can have the following theorem, which really tells you how to construct all of the generic singularities and bifurcations for spherical surfaces. So you take two analytic functions, kappa g and b, extend them holomorphically, then write down this holomorphic potential. This is a valid holomorphic potential for harmonic maps and spherical surfaces. Then we construct the harmonic map n and the spherical surface f using the DPW method that I described before. Then what you can say is, first of all, the geometric interpretation of kappa g along the curve y equals 0 is just the geodesic curvature of the curve n in S2. And the other function b is the speed of the curve f of x0. And then this list of conditions here you have on b and kappa g characterize all of these different types of singularities, which includes the generic singularities and the generic bifurcations. So for example, we can use this to construct the actual bifurcation from what's called a cuspidal beaks bifurcation, where on one side you have two cuspidal edges, and on the other side you have two swallowtails. Cuspidal edge becomes two swallowtails. So you can write down these potentials, check the condition when s equals 0, you get the condition for cuspidal beaks bifurcation, and when s is not 0, you get either this one or this one. And similarly, you can construct the what's called the cuspidal butterfly bifurcation using this family. So on this side you have a cuspidal edge, and on this side you have two swallowtails. So that the proofs of this about the generic bifurcations for spherical surfaces you can find in I'll tell you the reference in a moment. That's a recent paper I've written with Farid. What we showed there is that of the generic bifurcations for wavefronts, 3 of them, it's this and these 2, don't occur at all. These singularities don't occur at all for spherical surfaces. And the other 2, which is the ones I just showed you, they do occur as singularities, and so does the bifurcation between so from, for example, this to this also occurs in families. So these are the references for all of what I've been saying. You can find well, you can find references about the DPW method if you look, for example, in this paper, and I mean it goes back maybe 20-30 years, and you can find the work about the bifurcations in this paper here. Alright, so my next talk, the next part of my talk will be about maximal surfaces in the Heisenberg group.